Yeah, hello everyone. First talk of today is by David Glick from UC Davis on Everettian quantum gravity. Please.
Okay, thanks a lot. Thanks to the organizers for inviting me. This has been really cool and amazing setting. So thanks Baptiste, Annika, and Chris. So this talk is going to be a little different than the talks yesterday in that it's going to be more on the metaphysical issues and it's going to be less well developed. So this is definitely early stages, so I'm really eager to hear what you all think. So the starting point is going to be the Everettian multiverse picture of quantum mechanics as exemplified by David Wallace in his book of that title. I'll be mostly focusing on David Wallace here, but the sort of larger goal is to think about how we can incorporate quantum gravity into the Everettian picture more generally, but it is important that the kind of multiverse or many worlds view we're talking about here is one where the many worlds are emergent. They're not put in at the fundamental level, but there's something that naturally emerges from the fundamental ontology via decoherence. So that's what I'll mean by kind of Everettianism for the purposes of this talk, is that general framework. Okay. So that book is, very detailed and develops a lot of things, but certain metaphysical issues, I think, are not entirely clear in the Everettian multiverse, or the emergent multiverse picture. And my co-author, I should have said this paper is co-authored with my graduate student, Jerome Romagosa. One thing that we've been working on, that he's been working on especially, are questions like this one, which is, should we think of the worlds in Everett as branching in this way? This is sort of the usual way where we have a single past until decoherence occurs, and then we get some branching event. Say we're measuring the spin of an electron, right? Prior to the measurement, we've just got one world, and then we're going to get a branch on which it's up and a branch on which it's down. A somewhat an alternative view is a divergence view, where you say, actually, even prior to decoherence, there were two worlds. They were just qualitatively indistinguishable. So they're two perfectly similar worlds. And you might, even though the branching picture seems more obvious, given that decoherence is not something that occurs at a precise moment, it comes in degrees, that's something I'll come back to. You might think that this is a better picture for that reason, and also this might help with probabilities, given that you might have self-locating uncertainty prior to a branching event. So anyway, that's a larger debate that we were sort of thinking about around the same time I was wondering what to present here. And one issue that sort of gets mixed up in all this is what's the status of space-time as regards to these Everettian worlds? In particular, does each world have its own space-time, or are they in the same space-time in some way? And especially if you have the divergence view, you might be pushed toward thinking they're in different space-times. So what does Wallace say about this? Well, he says, I'll just read the quote, I guess. I've spoken throughout as if branching events play out against a fixed background space-time, and this is indeed what our current best theories of quantum mechanics, quantum field theory predicts. Other branches then are located in precisely the same space-time as our own. It's just that they're dynamically incapable of significantly affecting our world, and vice versa. So everything's in the same space-time, they're just overlaid and they're incapable of interacting because of decoherence. But then we have this suggestive remark. However, while this is true in our best current quantum theories, it is rather unlikely to survive the inclusion of gravity in those theories. So he's suggesting here that once we start thinking about quantum gravity, we'll have to say that different Everettian worlds have different space-times. So that's sort of the jumping off point here. And the argument that we're going to make here is just that this is in tension with other views that are part of this package that Wallace gives us for the emergent multiverse. And in particular, this claim, his space-time state realism, that fundamental reality is faithfully represented by density operators assigned to space-time regions. I'll go through each of these. The other claims as we'll see, I think are pretty plausible and modest, but we'll come back to those. Let me just flag something right away. You might be thinking to yourself, well, of course, space-time state realism can't be right in a quantum gravity setting because it says space-time is fundamental, and we know from the work of Chris and others that we should think of space-time as emergent in at least many approaches to quantum gravity. I think that argument is actually too quick. I think there is a way to think about space-time state realism that allows for emergent space-time. So I think this, what I'm calling the tetralemma here, this set of inconsistent claims is a better way to formulate things. And I hope that we can see that there might be problems even for other ways of thinking about the Everettian quantum mechanics. All right, but we're going to just, plan for the talk is just to go through those claims basically, and then talk about whether we can modify space-time state realism to accommodate gravity, and then sort of some more general remarks about how this stuff might extend once we drop space-time state realism. Okay, so what is space-time state realism? Well, again, the emergent multiverse picture is a two-level kind of theory. We have a fundamental level described by the universal quantum state. We have unitary evolution according to Schrodinger's equation. It's deterministic, it's precise, it's fully determinate. There's nothing fuzzy about what's going on at that level. But the emergent ontology is one where we get this multiverse of macro ontology, where we've got tables and chairs and all this good stuff. It's probabilistic or supports probabilities. It's imprecise in certain ways because it's coarse-grained, and it's determinate only for all practical purposes. You can look at my paper with Baptiste for more on that. Okay. So, question, what is this fundamental reality on this emergent multiverse picture? Well, there are at least three views that are well known in the literature. One is wave function realism. That fundamental reality consists of a field on a high-dimensional space that's local and separable. In the case of non-relativistic quantum mechanics, that's something like a configuration space. The Mad Dog Everettianism, Sean's view that fundamental reality is a vector in Hilbert space. And then Wallace's own view, the space-time state realism, is going to say fundamental reality consists of density operators assigned to regions of space-time. So because I'm sort of taking Wallace as our starting point here, I'll see what he says against these other views, and then we'll come back and see why space-time state realism is problematic later. Okay. So against wave function realism, Wallace and Timpson say that the problem is that it privileges the position basis. If we're thinking of, at least in terms of a configuration space, we're thinking in terms of positions. This is problematic, even arguably in non-relativistic quantum mechanics, but certainly once you get to quantum field theory, where oftentimes we don't even have the ability to represent things in configuration space. We might have a superposition of particle numbers. Now, it's worth noting that Alyssa Ney has responded to this and thinks of wave function realism in a more general way, that it's rather just the idea that sort of a schema that whenever you give me a non-local space, I'm going to find a higher dimensional space where I can restore locality and separability. And she argues you can do that even in quantum field theory. You can construct a space that is local and separable. We can talk more about that if you want, but it's not super important. What about the reality as a vector in Hilbert space, the Mad Dog Everettian view? I think basically Wallace's objection here, or complaint against this view, is that it somehow doesn't make explicit the structure of the quantum state. So here's one passage from his book. I mean, he's not directly, given the timeline, he's not directly addressing Mad Dog Everettianism here, but I think this is his general concern with that kind of approach. Wallace argues it becomes hard to see what justifies speaking of the quantum state as highly structured. A ray in Hilbert space is just an unstructured line, and all rays seem perfectly alike. So this is just too sparse of a fundamental ontology to give us any kind of way of visualizing or making explicit the structure. So, what should we think instead? Well, here's the closest thing we get to a statement of space-time state realism, and this is just in the framework, just taking very literally the framework of algebraic quantum field theory. We associate each region with a C-star algebra of operators representing the dynamical variables, and then the state rows of the region is just a positive linear functional on that algebra of observables that gives us the expectation values. So that's what he's arguing is a way of thinking about what it means to say that fundamentally reality is just described by the quantum state. So the way I'll just flag this briefly that I'll maybe vacillate between saying reality is these density operators on a space-time region and reality is faithfully represented is what I've said here. I think the best way to understand this is something like the most perspicuous description of reality is this one. Density operators assigned to space-time regions. It takes AQFT seriously, it doesn't privilege a particular basis, and it makes apparent the structure of the quantum state. Okay, so there's obviously more to be said, but that's the first piece, space-time state realism. All right, now moving to the quantum gravity piece, my conjecture, and as you'll see in a moment, my understanding of quantum gravity is pretty naive, so I'm open to being corrected here. My conjecture is that quantum gravity is going to give rise to superpositions of space-time geometry that have undergone decoherence. That's what I need for my argument, at least. Again, very naive here. It'd be nice to go through all the models of quantum gravity and show that this is true. I'm going to do something much simpler. This sort of thought experiment from Feynman is sort of what's motivating me to think this. That look, we can just do a double slit experiment and we just put a highly sensitive gravity detector behind the slit. And what we will get then, right, is a state that looks something like this, where one of these terms is saying it goes through slit 1, there's a gravitational field G, and a detector setting D1, and likewise for slit 2. And we're just going to get a superposition, straightforwardly, of different states of the gravitational field. And so given what we know about general relativity, that means we're going to get different space-time geometries entangled with the particle, in this case, going through the two slits. And I know that there's ongoing debate about whether gravitation alone is capable of engendering decoherence. I'm sort of sidestepping that here and just thinking that, look, certainly by the time you have a detection event, we have sufficient decoherence to say there are two branches. So that's going to be entangled with the state of the gravitational field here. So that seems pretty compelling to me, again, as sort of an outsider to the area. Wallace himself, though, seems to agree with this conjecture. This is just moving on from that same quote I had earlier. According to general relativity, space-time is dynamical and influenced by the distribution of matter. Superposition of macroscopic different states, therefore, should become entangled with spatial geometry, giving rise to superpositions of different geometry. So for this reason, I expect the true quantum state is a superposition of geometries. So once we have our theory of quantum gravity, this is going to fall out. Until someone in here convinces me otherwise, I think this seems like a plausible idea that quantum gravity is going to give us these superpositions of space-time geometry. I know there are a few exceptions, people who think that we can have a sort of classical understanding of gravity, combined interacting with quantum processes in certain ways, but I think this is a pretty widespread view. Okay, so that's quantum gravity. So then, I didn't realize that I needed this at first, but for the argument, I need to say not just that we're going to get different geometries, but that we're going to get different space-times. So I need a link between space-time and geometry. Again, I think this is going to be pretty plausible. There's obviously a big debate about what space-time is. You could be naive and just think it's sort of a double with the metric field. You could have a structuralist view where you say there are metrical relations between points that are nothing over and above the relations they stand in. You could have a functionalist view. Space-time is what space-time does, right? That's a popular view in the setting of quantum gravity. The point's going to be, on all of these views, the space-time is going to depend on the geometry, on the metrical field. Where I need to, this is another area I need to get a little more precise on exactly what I want to claim metaphysically here. But the idea is that they all say space-time in some way depends on geometry. Maybe it's something like existential dependence, where we say necessarily if I have a certain space-time, then I must have a certain geometry. All I need for my argument is this weaker claim that geometry supervenes on space-time. I can't have a change in geometry without a change in space-time. So that's all I actually need. I don't need the stronger existential dependence claim. But I think, again, that's pretty modest. I'm sure there's more to say here. Maybe you think this isn't so modest, but it seems to me plausible that distinct space-time geometries correspond to distinct spacetimes. The only view I can think that would really reject this is if you were like, your view of space-time was a bare manifold view, where you just say, space-time is just the points. Then it might be plausible to say, well, those points could be in a superposition of different geometries, but it would just be one space-time. That's sort of, just like, remember what Wallace says about ordinary Everettian worlds, is they're in the same space-time and they just don't interact. So maybe the geometries could be in the same space-time and just not interact. But I think you'd have to adopt a pretty idiosyncratic view of space-time to say that. I mean, Maudlin is sort of in the ballpark, but Maudlin thinks the metrical properties are held essentially. So even he wouldn't allow this, I don't think. Okay. Let's see what I'm doing on time. Oh, I need to go a little faster. Okay, cool. All right, well, that's fine. So where we are now is in standard Everettian quantum mechanics, it's underdetermined whether each Everettian world is associated with its own space-time, but if we assume what I'm calling QG in this space-time geometry link, then Everettian quantum mechanics is going to require each world to have its own space-time. This means that the level of space-time is at the multiverse level, not at the fundamental level. So we need to reject space-time state realism, which says space-time is at the fundamental level. And again, you might have thought, well, this is, again, just obvious. We know space-time is not fundamental in QG. But as I'll go on to now, I think that that's too quick a dismissal, because we can talk about modifying space-time state realism. Indeed, Wallace and Timpson mention quantum gravity in their paper and say, well, look, it could turn out that space-time is not fundamental, but that doesn't mean that space-time is not non-existent. It just means it's emergent. So why can't we take a view where we say, okay, space-time is not fundamental, but the story that we're telling, the space-time state realist story, is once we get to the level of space-time, we're going to have a QFT level description, these assignment of density operators to regions. It's going to give rise to a multiverse of macro worlds. Just like what they said in the fundamental case, we're just dropping the fundamentality claim. I don't think this works. So this would suggest a kind of two-level multiverse where we have some theory of quantum gravity that gives rise to a multiverse of spacetimes. So spacetimes come in at this level. Each one of those is understood according to spacetime state realism as giving us an assignment of density operators. And then we get a multiverse of macro worlds coming from there. This just doesn't seem plausible because, as we've already said, the configuration of macro objects is going to be entangled with the geometry. So this should really just collapse into one level. So I don't think it's tenable to say space-time state realism is true, just not fundamental. I don't think that'll work because, yeah, again, these two levels should collapse. We shouldn't have a two-level view. Okay. What's another way? Well, I found this quote in a footnote by a paper by Al Wilson, where he says, I haven't seen anyone really talking about how to adapt space-time state realism to quantum gravity, but the simplest extension would be to transfer what space-time state realism says about space-time over to whatever fundamental space hosts the fields posited by one's preferred theory of quantum gravity. So maybe we should modify it this way. Fundamental space consists of quantum gravitational fields defined on some fundamental space that we get from our theory of quantum gravity. Okay, I still have 10 minutes. Oh, I guess we started late. Okay, good. I'll have plenty of time then. So, what's wrong with this proposal? Well, I mean, even though, if you look at it, it's more of like a schema. It's saying that whatever the fundamental space is going to be given by this theory of quantum gravity, and even what the state is, what the fields are, it's going to be given by a theory of quantum gravity. It still seems to rule out some approaches. Again, those of you in this room who know a lot more about quantum gravity should correct me if I'm wrong on this stuff. But it seems to me that not all proposals for a theory of quantum gravity posit fundamental fields at all on a fundamental space. Causal set theory, for example, doesn't seem to clearly involve either of those things, a field or any kind of background arena in which things unfold. The other problem, I think, with this approach, where you say, okay, now what space-time state realism means is just whatever the fundamental arena of quantum gravity is, with whatever they say the fundamental state is, you kind of lose the difference between space-time state realism and the other approaches that are rivals to it. So, for example, remember the complaint against Sean's view against the Mad Dog Everettian. All Hilbert spaces of the same dimension are isomorphic, so differences between quantum systems can't be understood without additional structure. And absent additional structure, it's just featureless, unstructured object, where the quantum state is supposed to be something richly structured, very complex. I should have said this before, but of course it is worth noting that that Sean has this quantum mereology stuff that we heard about yesterday, which is a way to answer this objection. But at any rate, that's supposed to be the objection. It seems to me that you could say the same thing about an approach like applying this space-time state realism approach to a theory like causal set theory. That's also going to give us a fundamental ontology which is in some way structureless. The analogy is not perfect, but the idea was something like all causal sets of the same causal order are going to be isomorphic in some way. So in each element of a causal set is just totally unstructured. So the worry is, like, if you're really worried that your fundamental ontology has to be sort of illuminating the structure of the universe, you're not going to get much of that from an approach like causal set theory anyway. So to the extent that space-time state realism is compatible with all approaches to quantum gravity, it looks like it can no longer make that argument against rivals. All right, so where are we now? So space-time state realism, it seems to us, is not going to survive into quantum gravity. To survive would require modifying it such that it loses all content, basically. It's no longer going to be a viable alternative. So we should get rid of it. Are there some more general concerns with the metaphysics of Everettian quantum gravity? There's at least some problems on the horizon. Maybe these are just, classical intuitions that we need to get rid of. Maybe there's more. So, and these problems, again, these were sort of problems that Jerome, my collaborator, was thinking about in the context of ordinary EQM, but here they become really vivid because if we accept QG, SGL, and just EQM here just being the claim that when you have a superposition state that's undergone sufficient decoherence, those correspond to different worlds. Then we're going to get this claim that worlds inhabit distinct spacetimes, and this causes some problems for usual metaphysical ways of thinking. So I'll just briefly mention these two problems, and then I'll wrap up. Okay. So the first problem is the isolation problem. If distinct worlds exist in wholly distinct spacetimes, then distinct worlds are causally isolated from one another. But remember how decoherence works. We only get effective isolation. Decoherence is never, it's a process that admits of degrees. It's never complete. So even though in practice we can treat the worlds as completely isolated, they are not, strictly speaking, isolated from one another. So if they're not fully causally isolated from one another, then how can we say that they're in distinct spacetimes? It seems like we would have to reject the idea that being in the same spacetime is a necessary condition for causal influence, which a lot of people would think. Okay, thanks. That's the first one, a sort of related worry. Spacetime, being related spatiotemporally, is usually thought to be transitive. If A is spatially temporally related to B and B is spatial-temporally related to C, then A should be spatial-temporally related to C. That seems to fail here, right? Again, just think of the simple Feynman gravitational two-slit experiment here. It could be the case, it seems like the preparation event is spatio-temporally related to detection event 1. The preparation event is also spatio-temporally related to detection event 2, but the two detection events are in different spacetimes, right? They're in different spacetimes because there's a branching that occurs, and we're saying that different worlds live in different spacetimes. So again, it looks like at least a failure if we assume what most people think is a plausible condition, that spatial-temporal relation is transitive. Okay, so what I've tried to argue here is that these four claims are inconsistent, and given the sort of plausibility of these two, QG and SGL, if we want to be an Everettian about quantum gravity, we're going to have to replace space-time state realism with something else. The ways that we might modify it don't work. And even though, given that the argument is not just, oh, well, space-time is emergent, the ramifications might be more than just, Wallace is wrong. It might be that there are some problems lurking for any theory of Everettian quantum gravity. Okay, that's all I got. Thanks.
Okay, so thank you very much, David, and Jerome as well for this very nice talk. Let's look at the tetralemma once again. I think David and Jerome did a really nice job at kind of showing us that there is some kind of tension arising when we try to extend space-time state realism to the context of quantum gravity and Everettian quantum gravity in particular. I think I would like to hear maybe a little bit more about how these four claims actually come into tension with one another. So maybe is this meant to be really a genuine kind of inconsistency in the sense of a no-go theorem perhaps? Or is this some kind of weaker or looser kind of tension against perhaps a backdrop of some other reasonable assumptions? But setting this issue aside, I think I will focus the comment on two of those horns, I guess, of the tetralemma. So let's begin with the first one. About SSR, I would like to ask, what is actually the target here of the argument? So, in particular, what work does the word fundamental play in the formulation of the SSR? So let me try to paint a kind of picture here. One could say that space-time state realism works, I guess, just fine in the context of relativistic quantum field theory, modulo, let's say, the debates in that context. However, there is some kind of tension when we take in quantum gravity into the account, namely that space-time itself is likely going to be quantum or non-fundamental or something like that. However, perhaps SSR can still be some kind of effective ontology, right, at the level of RQFT. And so what is actually the genuine target of Dave's and Jerome's paper, right, would be SSR as applied to some kind of fundamental theory of quantum gravity. And the reason why I decided to set it up in this manner is that I think it's maybe quite faithful to how Wallace tends to think about philosophy of physics, right? Because he is a philosopher who has shown great appreciation to effective physics, right, and some kind of effective ontology. And so, yes, maybe space-time state realism too should be thought of as some kind of effective ontology that holds kind of in the context of either non-relativistic quantum mechanics or relativistic quantum field theory. That said, it can still be an interesting project to investigate how it extends further. So much about SSR. Let me also say something about SGL. I think SGL actually touches on some issues that are discussed by philosophers of physics quite a lot, and namely in the context of the whole argument. So I think there are two ways in which SGL relates to this literature. I mean, on the one hand, there is the question of what we mean by distinct space-time geometries, right? Are these meant to be set theoretically distinct Lorentzian manifolds, or some kind of structurally non-similar, non-diffeomorphic Lorentzian manifolds? And this question is taken up in the Weatherall paper on the whole argument, also in the Dougherty and the Hott papers on this literature. So it's something that philosophers of physics themselves don't fully agree on, I think. So that's one way in which this debate bears on SGL. And the second connection to the whole argument literature is actually through Fletcher's RDMI. So RDMI is a principle that Fletcher kind of formulates in his paper on representational capacities and the whole argument. And it's the thesis that states that if two models of a physical theory are not mathematically equivalent, then it's not the case that there is a unique physical state of affairs that they represent equally well. And to me, this prima facie sounds very similar to SGL. So what to make of it? Well, the problem is that Fletcher actually rejects RDMI. He has an argument against it. And actually Pooley and Reed agree with that argument. But then still they propose something else that they call RDMI star. So the literature kind of grows and becomes quite complex. But I wouldn't want to go into that. So essentially I would say, yeah, it's quite a can of worms. So yeah, SGL might look innocent kind of at the first sight, but it brings up some deep philosophical issues. So just to kind of briefly summarize Fletcher's argument against RDMI, he asks us to consider a mathematical Schwarzschild spacetime and its scaled up version that results simply from multiplying the metric by a constant. And then he says that these two models are mathematically inequivalent. However, if we appropriately choose units, both of these mathematical spacetimes can represent equally well any physical Schwarzschild spacetime whatsoever. And this kind of undermines the thesis of the RDMI. So I guess my question for David here would be, I mean, first of all, are these connections, or do you find these connections to the whole argument literature fruitful or insightful to the status of SGL? And in particular, can we view SGL just as a special case of RDMI? And if yes, would you have a response to Fletcher's argument here? Yes, so thank you very much.
I'll take a couple minutes. Thanks for those comments, Mate. I'll have to think a little more about them to give a full response, but let me just say a few things right now. On SSR, yeah, I think this is a good question. Sort of, what is the core kind of content of space-time state realism? Because yeah, it's fine. Like in some ways, there's nothing wrong. We don't think there's anything wrong with saying, yeah, the ontology of quantum field theory is density operators on space-time. So what we're taking issue with, I guess, is that somehow being this sort of that being the fundamental ontology that gives rise to the multiverse. And the idea was, even if we say it's just relatively fundamental, so we try to preserve, the structure that we have a single space-time at some level of description with these density operators on it, and then we have a multiverse of macro worlds. That can't even be true at the relative level, or the emergent level. So it's not just the claim about the sort of first order claim, what is the ontology of QFT? Like, that's a debate, we can have that debate, but there's something else going on, which is its role in EQM as being this sort of unifier or common ground, if you like, for the multiverse. And that's the part that we think won't work. So that could maybe be divorced from just the first order question of what the ontology of QFT is. But you're right, like we need to maybe make that more precise in how we formulate SSR. The second thing, on the whole argument, that stuff's really cool. I'm not as up on the current literature on the whole argument as I should be. But let me just say this in sort of defense of SGL, and again, I might have formulated it stronger than what we need for the argument. All we need for the argument, right, is that if we take seriously a quantum theory of gravity, we're going to get superpositions of geometries that give rise to distinct space-time. It could be the case that some distinct geometries correspond to the same space-time, but at least the sort of, think about, the Feynman case, or a case where we have just very different macro ontology configurations. Those are going to be radically different geometries. At least those we need to count as distinct spacetimes, and I think that's all we need for the argument. So I'd be hoping we can kind of sidestep subtleties about like an arbitrary factor being applied to G mu nu or something. Like, I would hope to at least not have to get into that and not have to endorse a claim as strong as, what was it, the Fletcher claim that you mentioned. So that's how I want to go, but yeah, we'll talk more. Thanks.
Thanks, David, that was great. I just had an idea about the isolation worry. So, okay, we have different worlds, each with a different space-time. Will it bother that the worlds may be causally connected when the space-time should not be causally connected?
Yes.
I was wondering, perhaps you can make a Wilson move, because if I remember correctly, for him, the worlds, strictly speaking, are causally disconnected.
Right.
Because the connection goes through the more fundamental quantum state.
Right.
Right. So it's because you use big G grounding, so you have the worlds grounded. So I think maybe that will be aware of this way. I mean, that's kind of a very specific kind of EQM.
Yeah.
But yeah, what do you think? Maybe there
that's
interesting moves there.
Yeah, no, that's good. Yeah, you're right. So Al Wilson, partially because he's got this weird modal project that he has in mind for the worlds, but it's important to him the worlds don't causally interact, even though he's the divergence theorist. And he recognizes that decoherence is not complete. So if there's sort of negligible interference between worlds, he wants to explain that, right, in terms of some common ground kind of story. Yeah, I mean, I guess that seems to us to be a cost. That, you know, like we have, before decoherence, we have interactions and we think of them as causal, and then somehow after decoherence, they become non-causal. I don't know, maybe that wouldn't come out on his view. I mean, he would say there's only in-world causation, yeah. I don't know, I'll just say that that seems like a cost to have to endorse that. Leads to maybe some counterintuitive consequences. Yeah, I mean, you might worry that it'll overgenerate, lead to causal nihilism, but
yeah, I guess we would have to buy his big picture, but I suspect for him, he will find that he will have a ready answer.
yes,
probably
I agree. Yeah, he wouldn't be worried about it, but again, he has other motivations to hold that as well. Thanks, though.
Just quick, is the L for link? I forgot what L stands for.
Yes,
L?
yes.
So, I mean, I think the answer to my question is going to be that this is all in the context of the space-time state realism. But just consider that some of the arguments you gave seem sort of to make too much of a classical assumption or bring in too many classical considerations. Because consider the PPL, which is the particle position link. The same thing sort of goes. Well, the one particle can't have two positions, right? So now what do I say about superpositions? They can't be a particle, right? It seems like a very analogous thing.
Yeah.
But the problem is you're thinking about particles classically. They're quantum particles. One would say the same thing here. This is a quantum space-time.
Yeah.
So one wouldn't expect this.
Nice.
I can sort of see then one might bring the question, right, but is a quantum can you have space-time state realism, quantum superposition, in a quantum space-time which has superpositions? But some of the arguments you were bringing did seem to just assume space-time was a kind of classical thing. So I worry a little bit about that.
No, that's a nice point. Yeah, I mean, I think part of the reason, you're probably right that there's an oversight there. I think part of the reason was from the Everettian kind of perspective, you're already inclined to think, well, a superposition of classical states of affairs is understood as two, right, worlds that are quasi-classical. So maybe I was already thinking that. Yeah.
After decoherence.
After decoherence. That's right. So prior to decoherence, you could just say it's a quantum soup of some kind. Yeah. So yeah, maybe you could say that about geometries too. There's single space-time in a quantum superposition of geometries.
Yeah, okay, so anyway, a general comment.
No, yeah.
We are talking about quantum space-time, so, yeah.
Good. Yeah,
We should
yeah.
expect things to be the same.
Yeah, I'll have to think more about it, but yeah, I was thinking in an Everettian setting, at least it would be plausible to think this way. But yeah, you're right. Even prior to decoherence, even in Everettian, but I have to say it can be in a superposition. Good. Yeah, think about that.
Yeah. So just on the argument that you made, where you were saying that there wasn't a space in causal set theory to take density operators or whatever the analogous type Wallace view would be down there. It just seemed to me like there was such a space.
Okay, even in causal set theory?
And the causal set theorists are interested in spreading quantum fields over that thing. I mean, they haven't quite done it yet, but they're trying. But then more generally, I just thought, I mean, shouldn't there always be something down there that we can spread some
yeah, I guess
fields over? Like, I guess I'm worried that there was more here to think about, at least.
Oh, I'm sure. Yeah, I'm sure there is.
Like the causal set case, I think they do think that they can take the field as well.
Okay, yeah, I'm happy to defer to you on that because, yeah, I'm by no means an expert in causal set theory. I guess I was thinking it's just, this partial order on these nodes. There's no background space. That's what I was thinking. There's no obvious field.
Yeah, I guess. Why do you need a background space? Why can't you just drop it onto Why do you need a background space? Why can't you just drop it onto the causal sets? Like, why isn't that relatively analogous to the space-time state realism stuff?
Yeah, I
Is
mean,
it that you want something kind of like, yeah, space-time thing down over?
I mean, again, they're kind of, there's two kind of worries that we have for this kind of Wilson idea that we can sort of generalize space-time state. Yeah, one is it's either going to be sort of vacuous or it's going to constrain what a theory of quantum gravity looks like. This was supposed to be making a constraining point, and then the other point is if you're too flexible about what the fundamental ontology could be, and still call it an analog to space-time state realism, then you lose what's distinctive about space-time state realism.
I guess I'm not sure about that. I was thinking, like, if you think of this move as more like functionalizing the space-time state realism type view, that it's just like whatever plays the space role down there, whatever plays the density operator role, sort of like structurally the right kind of view, but not exactly hitting density operators to space-time.
Yeah. Okay, good.
But I don't know if that strips it of content. I mean, maybe it does if it's like too literal, but it's not obvious that there isn't a version of this view that you can't specify. It's still got some content.
Okay. Yeah, thanks.
Yeah, it's very interesting. I was just wondering, for instance, it should be rather a point of going forwards in Everettian quantum gravity. I mean, after all, quantum gravity is very ambiguous, right? You can mean all kind of scales with this, and not always particularly kind of the highest degree. So in that sense, I think it's correct. Quantum gravity is still, and I would kind of vouch for seeing this as more of a quantum-up project, where you can look at the next interesting frontier, right? Because all kind of converging approach, they might agree on that you eventually get some form of effective geometry superposition.
Yeah.
But yeah, that's not the end of the story, right? And also the other way around, I think you get a very interesting phenomenon if you kind of do the bottom-up approach. Because, for instance, if you just take this PIE experiment, I think he was referring to yesterday, about just two masses, right, which are somehow in superposition interacting. And you can already model this with the space-time superposition. And however, you can also bring them together again, these masses, in one space-time. And so there's this exciting question, what does it really even mean if you have space-time superposition to kind of come together with these different space-times again? So the exciting question of identity across space-time and superposition. Yeah, how do you even kind of set this up at this lower energy scales, right? And then I think if you approach it like this, yeah, I think it's even more interesting than it's now. I mean, I think now it's great, but I think in terms of humility, one could phrase it more as torpid Everettian gravity in terms of having somehow additional topics, but would look at these kind of bottom-up cases like the GIE experiment.
Okay. Yeah. Yeah, I'm not sure I fully understand.
I mean, just I mean, just as an example, right? If I have one mass which is like this one superposition, another mass, and they're kind of interacting, like let's say Newtonian potential, right?
Yeah.
You can model this in some form of superposition of kind of Newtonian geometric space-time. However, in the experiment, you bring it, you kind of look for some entanglement pattern for this, and so you really get back into results with one space-time. So what's happening there, right?
Yeah.
And I think that's, it was related to this, there's this so-called quantum hold argument, right? So not just hold argument for one branch, but cross branches, right? So I think this is just, this could just be added to this project, I think, in a way.
Yeah.
Yeah, so yeah.
Yeah, no, that sounds really interesting. Yeah, I wouldn't know if I could make the same argument or if it would be a different argument about this sort of problem with space-time state realism in a sort of lower energy scale. I mean, I don't know if this is relevant. Another thing that Walsh, the only other mention of gravity in their paper is they mention in semi-classical quantum gravity, we still have, they say something like, the only way to understand semi-classical quantum gravity is to understand it is an assignment of density operators to regions of space. So they're thinking, like, again, that at that level, at least, their story is going to work. But I wonder if some of the things you're mentioning actually might say, even at that level, the lower energy level, we can already make an argument of this effect.
Yeah.
Which would be a cool result.
Yeah.
Yeah. No, I like that. Thanks.
Thanks, David. I really enjoyed the argument you laid out. I actually would just appreciate you to go through a little more slowly why you have the two emergent levels. I didn't understand that really because I was imagining that you would just have decoherence and then you would have the worlds with the different space-time geometries and then you would apply SSR just to one world at a time.
Yeah, good. I think this is something we need to be more clear about. It's sort of, the idea is like, what's the essence, this sort of came out in Max's question too, like, what is the essence of SSR? And we were thinking like, it's not the claim that this level is fundamental, but it's something like the claim that it gives rise to a multiverse of macro states of affairs. So on the standard version of SSR, without gravity, right, there's just one space-time. It has these density operators assigned to regions, and then that gives rise to the multiverse of macro Everettian worlds. And so what we were thinking is like, even if you situate that as a non-fundamental level, you're still going to get this sort of branching structure. But yeah, you could have like that's what I was saying, like a weaker understanding of SSR would just be like, that's just the first order correct ontology for QFT. But then there'd be just sort of maybe one here, you wouldn't get further branching here. I take it that's your kind of thought, right? Is that making sense at all?
Or maybe I'm not understanding the original SSR as generating the worlds. I was imagining that decoherence generates the worlds, not SSR, and then once you get the worlds, then you apply to each world SSR. So maybe I'm also just misunderstanding what the project was originally with SSR.
Good, yeah, you're right. That's good. I think you're right. The decoherence is what's generating the worlds. Combined with the idea that the way to interpret what's going on at the quantum field theory level is this multiverse interpretation of what's going on once we have decoherence. So maybe we're baking that into SSR as well.
Whereas I want to keep them separate.
Yeah, good. Probably need to think more about that. Yeah, there's a lot of, part of what's making this hard for me to get my head around at least is like, there's different kinds of emergence going on. There's sort of an interpretive emergence, where it's like, okay, when I have stable decoherent superpositions, then that gives rise to a multiverse, but that's sort of interpretational, where there's this dynamical thing going on with decoherence. And so, yeah, there's sort of horizontal and vertical stuff. Yeah.
Thank you, it was very interesting. So I think my question is like a follow-up to what Sam was asking. And I would appreciate if you could elaborate a bit more why you specifically focus on causal set theory as a case in which you want to say that space-time set realism, especially in the way in which Wilson was like trying to promote a space-time state realism star potentially in quantum gravity. So on the one hand, it's definitely true that physicists working on causal set theory are trying to put QFT on this structure. So you may want to have a motivation to say, do we really need the space-time as we typically think about to have a space-time realism star in CST? And on the other hand, why you would focus on causal set theory in order to assess this, especially with respect to the problem of securing an Everettian quantum gravity approach. So that I think I missed some points in there.
Good, yeah. The thought was just that, I was thinking that this kind of approach, again, there are multiple worries, but the worry that I was reading causal set theory and was just that, like, is this leaving hostages to fortune? Is it making a bet about what a theory of quantum gravity will look like? Namely, that it will provide a space with a field on it. And again, it sounds like I need to think more about whether causal set theory really is a counterexample to that. But that was the first thing that popped into my mind as potentially a counterexample, a way that we might end up with a theory of quantum gravity that doesn't obviously provide a field on a space, where some of the other approaches to quantum gravity, loop quantum gravity, string theory, I think would fit more naturally with this way of thinking. So it wasn't that I'm certainly not betting on causal set theory being the true theory of quantum gravity. It's just, yeah, I was just trying to make the point that we don't want to modify space-time state realism in a way that's placing such bets. But if there's a better example, you think of a potential counterexample to this, that'd be great.
Yeah, I guess I was wondering how much this should be as a theory-building principle or not, and so whether you want something that works for all these approaches or not. What's the motivation?
Oh yeah. Oh good. Yeah. Yeah. You might think it's not a bad thing to just, place your bet on a certain approach. I guess I was thinking, that would be a cost, that we wouldn't want to do that in how we think about space-time state realism. But yeah, you're right. Maybe that's fine. Yeah. Chris?
Thank you. Maybe this is a little bit too simplistic, but sometimes I like the simplistic approaches to get us focused on what's really at issue. So when I look at your tetralemma with this simplistic kind of glasses, I think isn't the answer obvious? I mean, what's all the fuss about? It's obviously SSR that needs to go here.
Yes.
And so we need to reconsider what is SSR trying to do. SSR is trying to be realist about quantum theory, right? We're going to say what that now means for there to be in the world. And the same thing done by wave function realism or Everettianism. So they're all trying to sort of articulate a bit more specifically what it is to be a realist about a quantum theory, I think.
Yes.
Now, SSR is not going to work because if we don't have this sort of standard quantum fields on space-time kind of theory, that's just not the right way to articulate what we should be realists about.
Good.
Wave function realism clearly needs to be generalized because it's sort of privileges, position, and so forth, for the reasons you've articulated. Everettianism doesn't seem to kind of have enough structure, perhaps, to get us everything we want. So the answer for me is we just need to sort of look with a realist ambition to a more generalized conception of what it is to be a quantum theory. And if we do that, then we are going to interpret this general sort of quantum theory realistically, and that will tell us what needs to be in place of SSR.
Yeah.
Isn't that what makes sense?
Right. Just be a realist about whatever theory of quantum gravity we end up with.
But it means now we have to think, in order to make this research program a bit more concrete, we need to think about what it is to be a quantum theory.
I see.
It's not having or postulating quantum fields on space-times, or something like that.
Yeah.
So we must have a conception of what quantum theories are that's general enough to make it to quantum gravity. And when we do that, this will tell us what needs to be in place of SSR.
Okay, I see. So you're not saying I think I misunderstood you at first. I thought you were saying wait for the theory of quantum gravity and then just be a standard realist about it. You're rather saying, no, even now we should be able to understand quantum theory in a way that's general enough to account for possible theories of quantum gravity. I take it that's kind of what I was trying to do here, is to say that space-time state realism isn't going to work, And there might be some more, general worries again if I'm not in Everettian. But yeah, I don't know if you don't like any of those three approaches, is there more we can say about that? What it is to be a quantum theory in general?
I think we have to do that. It's not something we're going to be able to do after we have a quantum theory of gravity. That's a step that's necessary to sort of get clear what it is in the first place to have a quantum theory of gravity. So that should be the first step in our project of quantum gravity, is to sort of have a clear-headed understanding of what we're looking for. What's that theory going to be like? What will qualify successfully as a quantum theory of gravity? And once we have that, that's SSR is going to be replaced appropriately. That's very general.
I think I'm sympathetic to that. Yeah.
Okay. Nick doesn't think we should proceed that way.
Oh.
I guess maybe also, I guess I have like two slightly different things. But like one thing I was thinking of is that a lot of people seem like Nick and me and Sam to some extent seem to have variations of complaint with the focus that she seems to have on space-time. And I was wondering if that's the actual, or like on this notion of grounds. And I was wondering if that's really what you need to argue against SSR. Because if you look at SSR, it's this claim, right, that you have there. Fundamental reality is frequently represented by the encyclopedias assigned to space-time regions. I don't think it's the space-time part that's problematic in quantum gravity. It's the assigned to regions part that's problematic in quantum gravity. Because even if you have quantum space-time, for example, going back to what Nick was saying, one thing that you will presumably, under anything that at least I personally can imagine is going to be the specification of that, you won't be able to assign stuff to regions in any sensible way, exactly because regions won't make any sense in that thing, because you will have the exact thing you're describing, superpositions of stuff. And even if you were able to, fix or abstain from the causal set stuff, that's kind of weird because it's the causal sets are classical and there's no quantum theory. But I would assume, maybe I should refer to you guys know more than me about this, but I would assume a quantum theory would involve superpositions of causal sets. And then you will have the exact same problem. Even if you can make sense of fields on the causal set, the problem is that you will never have any fundamental assignment of density matrices to nodes of the causal set, because there won't be such a thing as a univocal notion of the node of the causal set, just as there is no univocal notion of space, of region here. Because they're allowed to fluctuate, and once they're allowed to fluctuate, you're kind of done for. Things are annoying like that. So instead of focusing on and you wouldn't even need really an SGL anymore at the point. You just need to basically be allowed to assume that regions are allowed to fluctuate, and if regions are allowed to fluctuate, you cannot assign things to them, which is very straightforward, because if something moves, you cannot just say it's here if it moves,
Yeah. No, I like that. That idea of region in general. I mean, you might, one way you might understand that is, think about the complaint against Mad Dog Everettianism, he wants there to be structure, where structure is understood in this way of assigning things to regions. And you might say, well, that's just, that conception of structure is not plausible in the setting of quantum gravity.
Yeah, exactly.
Yeah,
you won't be able to have because basically what they're asking for if you're abstract away from the space is that they want some locality structure. They want to be able to represent it on the operator algebra, basically. Right? That's what they do when they think about the DFT example. They're taking the Poincaré and representing it on an operator algebra, and they're it induces all these relations. And that's the thing that presumably you will have trouble doing in any sensible way in the theory of gravity. You might be able to have this formally, but it won't map to that stuff. And another thing, if I can, that is, I think, close to what Sachi was asking, so maybe absolutely the same. I was also puzzled by these two levels, the complaint about the two-level thing, because my thought was extremely flat-footed that quantum gravity is kind of peculiar compared to a lot of quantum theories, that there is basically a hierarchy of forces between the fields of the standard model, the gravitational fields, such that it is much weaker. So in quantum gravity, you actually have a situation where you take something that looks like classical limit, and the classical limit involves quantum field theory or space-time instead of an actual classical theory, because that's not classical theory, it's a quantum field theory. And I didn't really understand why instead they should, like this somehow should not be possible to do in this framework, and they should collapse into one level, which I thought was
Yeah, they're not necessarily going to collapse into one level. The idea is that you're not going to get more worlds when you move from the QFT level to the macro level. There certainly are distinct levels there. There's a quantum classical transition. There's many levels, right? But the idea was that if you think space-time state realism is involved with, again, this is what it says if they're just one of these. So if you just try to move that same story to a non-fundamental level, that's not going to work because this picture is implausible. But yeah, there would still be levels. So the collapsing is just in terms of the generation of multiverses. But yeah, thanks. Yeah, I really like the point.
Okay, we'll take two last questions. So
More of a comment, I guess, but I'll just say this talk is a wonderful argument in favor of Mad Dog Everettian.
Yeah, I was thinking you might
appreciate that. Because all of these problems go away. They all come from trying to force classical notions of space-time and fields and things like that onto a quantum state where they don't fit very well. And if you just say, I have a state, and I use mereology to factorize it into system and environment, and I get branching, and once there is a branch, I look for the best fit classical geometry, everything's good.
Yeah. No, I was thinking you would say that. Yeah, no, and you know, I was sort of saying this to Enrico, like you might think that another way of putting what's going wrong here is that Walsh is operating with a particular conception of what structure is, and that's sort of maybe a sort of classical or at least QFT level understanding of things, and yeah, we need to be more liberal on what it would mean to recover structure. Yeah, good. So yeah, I think that's right. We should talk more because one thing I wanted to think more about in regards to your view is sort of whether we need space and time. We need to be talking about space and time rather than space-time in some of this story. But yeah, we'll maybe have that conversation later.
last question.
Thank you. Well, it's highly bracketing that thought. This is sort of coming back to what Neil said, but also part of what Manny was saying about the role that fundamentality is doing here. I mean, so the case is that Niels is talking about sort of experiments where you imagine having a sort of microgram object. It basically is not microscopic, and then a quantum superposition, and that's sort of the goals of the experiment. And what he's thinking about is it's in superposition, so each one is connected to a Newtonian potential. Think about it as a Newtonian metric, it's in GR. And then the experiment's kind of probing what effects that has. But that seems like not a problematic case here if we entirely ignore what Guy said, because the things I'm just saying kind of make sense according to his talk, but ignoring that. So, you know, I'll try and find some other speakers to ignore this question, but I'm not the only one who thinks this way. This is quite a common way of sort of thinking. You can actually understand those fields as excitations of gravitons in a Minkowski spacetime. So that's why this case is sort of I think, interesting because we don't, you have the superpositions of geometries, but you have a way of understanding them where you don't have these problems because you're just thinking about it as a Minkowski background, and you can analyze the geometry as an excitation.
I see.
The linear gravitational.
And so then you'd be able to say there's just one space-time there.
If you like, yeah, it's Minkowski space-time that's doing work. So the fundamental is, I think there's another word, so the fundamental is doing some work there. I think it has to be kind of pushing you past that regime to sort of beyond sort of linear gravity onto linear gravity, graviton thing.
Yep.
That's how I would think about it.
Yeah, I just have to think more about that.
Oh, I also meant to say, you know, I read these passages in Wallace as well. I was like, I don't know how to think about that, so I really kind of appreciated this talk.
Okay, good. It's not just me then.
Yeah, sorry. Well, both of the things I said sounded kind of negative, but actually it's because I really appreciate this. Yeah.
Thank you.
Okay.